Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. I hope all of you in a good condition. Welcome to International Conference on Agriculture, Food and Environment 2023. Okay, let me introduce myself. I am Mochamad Asrofi from University of Jember, especially from Department of Mechanical Engineering, Faculty of Engineering. In this chance and in this time, I want to present of my research about edible film biocomposite based on cassava starch, soy lecithin reinforced by sugarcane bagasse fiber, mechanical, morphological, and moisture properties. In my outline in this presentation, there are 5 sections in here. The first one is introduction, and the next materials, next method, results and discussion, and the last one is conclusion. Okay, from introduction, we know that in this picture, this is plastic waste in the ocean. Plastic waste is one of the main problems in every country, especially in Indonesia. This is evidenced by one of the research from Jambek et al. 2015 about the plastic waste in ocean. They report that Indonesia is the second biggest country producing synthetic plastic waste in the ocean. This is urgent. We know that in the map, the brown color is in Indonesian area. This is very urgent of plastic waste in Indonesia. So we hope our research become one solution later, especially in biodegradable and biocompostable plastic. Okay, some solutions to overcome the waste problem, including the first is sorting and recycling plastic waste, and the second one is turning synthetic plastic waste into energy, and the next one is creating environmentally friendly plastic, or we can call biodegradable and biocompostable plastic, and the last one is other solution. From some solution, our team, our researchers, our researchers choose the creating environmentally friendly plastic, or we can call biodegradable and biocompostable, or we can call edible film biocomposite. For example, the illustration of biodegradable and biocompostable plastic, like in this picture, in the right, like this, the illustration from newsberkeley.edu. This is before compost, and this is after compost, 3 days. Yeah. So 3 days, the plastic become compostable. Before we do this research, we have to collect some literature review or previous research. There are 3 previous research which can support our research. The first one is from Sabari et al. 2017, and the second one from Asrofi et al. 2020, and the last one is Cheng et al. 2023. And this is the support of our research. Okay, before we do our research, of course, we prepare our materials. The first one is cassava starch, or we can call tapioca flour with brand 99. And the second one is granular soy lecithin with total carbohydrate 8.2 grams. These two materials as a matrix of edible film biocomposite. And the next one is sugarcane bagasse as a pillar or reinforcement of biocomposite. And the last one is sodium hydroxide NaOH and aqueous for chemical treatment, namely alkalization in the sugarcane bagasse fiber product. Okay, if we have already prepared the materials, we next to prepare the sugarcane bagasse fiber. The first one, sugarcane bagasse waste, was purchased from a seller, especially in Jember region. Yeah. After that, fiber was weighed as much as 10 grams, and after that, we move to alkalization process of 10% sodium hydroxide for 4 hours. After that, the fiber was dried in drying oven for 20 hours at 50 degrees Celsius until constant weight. After that, we got a final product of sugarcane bagasse fiber as a pillar, like this picture in the final product, like paper, I think. Okay, if we have already prepared the fiber, we move to the production of edible film biocomposite. The first one, we mix cassava starch, soy lecithin, glycerol, and distilled butter were dissolved in hot plate magnetic stirrer at 400 RPM for 10 minutes. And after that, we mix with the fiber, or we can call sugarcane bagasse fiber, according to the variation of fiber. In this research, we varied the fiber as a 1 to 3% from the start day weight. After that, the solution or the biocomposite mixture we cast to the rectangular glass mold, yes, like this, yeah, and dried in drying oven at 40 degrees Celsius for 24 hours until become a biocomposite or bioplastic product. And after we got the product, we characterize, we test with the tensile test to determine the tensile strength, modulus of elasticity and elongation at break, and also fracture morphology by scanning electron microscope to determine adhesion bonding, fiber distribution, and agglomerate fiber in the matrix. And the last one test is moisture absorption test to determine the moisture resistance. Okay, from results and education, especially in tensile properties. This picture in the left is ultimate tensile strength, and the right is elongation at rate. We know that tensile strength is the limit of the ability of a material to withstand tensile loads obtained by the product before fracture. The mechanical the mechanical properties of biocomposite depend on the adhesion bonding or interaction between matrix and fiber. So the modified the fiber and matrix is become one factor to improve the properties of the biocomposite. Come back to the picture. From this picture, we know the addition of sugarcane bagasse fiber in the matrix of cassava starch and soy lecithin improve or increase the tensile strength. I mean ultimate tensile strength in here. The highest tensile strength was in the SPL 2%, the addition of fiber. This is indicate there is a good interaction between matrix and fiber. But in the addition, 3% of fiber, the ultimate tensile strength decrease. This is indicate maybe due to the agglomerated fiber in the matrix of the fiber. So the best result, the best value of ultimate tensile strength was in the addition 2% of sugarcane bulbous fiber in the cassava starch and lecithin matrix. And the second one is elongation at break. The elongation at break to determine the what we can say the brittleness, the what we can elasticity of the biocomposite film. The addition of the fiber decrease the elongation at break because the addition of fiber increase the brittleness of this biocomposite film. And the last one is modulus elasticity. The addition of fiber to the matrix cassava starch and lecithin increase the modulus of elasticity. The highest modulus also in 2% the addition of matrix. The addition of sugarcane bulbous fiber in the matrix with 0.5 to 3 MPa. This is indicated that due to the good interaction between matrix and fiber. So the tensile properties are also supported by the scanning electron microscope results. We know that in 2% there is a good interaction with addition bonding between matrix and fiber. Conversely, in 3% there are many void, many hole. We can see in the picture and with the label B, this is agglomerated fiber. So this is the one of the factor decrease in tensile strength of the composite. The moisture absorption also support the tensile and scanning electron microscope result. We know that this feature is the moisture absorption percentage. It can be seen that as the addition of sugarcane bulbous fiber into matrix, so a decrease in moisture absorption, or we can call the lowest moisture absorption was in SPL 2%. This is indicate that there are a correlation between tensile strength, moisture absorption, and fracture morphology. The best result in the addition of sugarcane bulbous fiber 2% in the matrix cassava starch and lecithin. So from all of analysis, we can conclude that the edible film biocomposite, or we can call biocomposite, based cassava starch and lecithin, reinforced by sugarcane bulbous fiber, was successfully made through solution casting process. The addition of mass fraction of fiber in the matrix affect the value of tensile strength. The highest tensile strength is found in the 2% variation with a tensile strength result of 0.829 MPa. This is evidenced by good bond between matrix and fiber through same observation. In addition, the addition of fiber in the matrix increase the moisture resistance. For future research, I think it is necessary to pay attention about composition and fabrication when mixing between matrix and fiber, cassava starch, lecithin, and the fiber to produce edible film biocomposite plastic. The author thanks to University of Jember for supporting the funding of this research. And if you have any question or research collaboration, please send them to us from technique@uneds.ac.id. Thanks for attention, and I say wassalamualaikum warahmatullahi wabarakatuh. See you and next time.